Howdy, people. We start a new unit today, and that unit is called Dynamics. All right, it captures well, a lot of material, and all that material centers on sort of a fundamental question. We've taken for granted the fact that things, well, that objects, what I sort of referred to here is do things. Objects, what I'm really getting at is objects can move in different ways. And we've talked quite a bit about that. Objects can move with constant velocities. Objects can move with constant accelerations. There are more complicated cases where objects can have non-constant accelerations. We don't look at those cases because they're more mathematically difficult than we're really ready for. But the question in this unit is, what is it that's responsible for an object moving in the way that it, or the ways that it does? All right, and the big answer to this question, how do you know what an object will do? What I'm really asking is, what determines if and how an object moves? Well, the one-word answer to that question is forces. A better answer to that question. So we're going to look at a bunch of cases, and one of them is this. Undo. One of them is this. Let's look at a case where an object, well, let's just say case one. Here's an object, and, well, let's say that there is a force acting on it like that. Okay? Well, that object does something. You actually know this. We would say that in this case, an unbalanced force acts on this object. All right, there's an unbalanced force to the right. Okay? As opposed to a case like this, where, let's call this case 2, we could have a force like this, F1, and a force like this, F2. And in this case, I would say 2 equal and opposite forces act on this object. Okay? 2 very different things happen. Okay? And we know this already. I think a lot of us do. We've mentioned this in our discussions of free fall, and really our sort of preliminary look-ahead discussions as to why things do what they do. So 2 very different things happen. And they happen as a result of either this, an unbalanced force, or this. When we call it equal and opposite forces, we can sort of say that this is a balanced forces case. Okay, so what's the difference? Well, this object you know what it does? Same thing that an object in, that here's a mass, and there's a gravitational force that acts like that, and gravity's the only force acting on an object. We said that's the criteria for an object in free fall. And what objects in free fall do? Well, they do in general the same thing that this object would do. We'd say this object accelerates. Conversely, over here, this object does not accelerate. That's the entire kind of basis of this entire unit. Objects either accelerate or they don't. Every object in the universe right now, depending on what we call your frame of reference, is either accelerating or it isn't. And if it isn't, it's because of a situation, at least in some way, comparable to this. Because, well, there are what we call balanced forces acting on the object. Or we can say all the forces on the object are quote-unquote balanced. Any object that is accelerating, it's because of this. It's because there's an unbalanced force that acts on the object. Okay, now, does it have to be just one force or two forces acting on an object? Of course not. All right, so let's look at a few more cases. Let's look at a case like this. Here's our object again. Let's say, well, let's go a little bit deeper here and say, well, let's say that there's a force like this and a force like, we'll call it F1, and a force like this. Call that F2. Now, first of all, when we say F, we're referring to a force. And what is a force? Any push or pull. Push or pull. Okay? And where those forces come from, what we can characterize them or what we can name them, that's not so important quite yet. All right? What is a little bit important, I suppose, is that we define the unit that will measure forces. And the metric unit of force is called the Newton. Okay, the English unit of force is called the pound. All right, so, but we're going to talk about forces in newtons. So let's say that this object has two forces on it. That looks like maybe it's 4 newtons. Okay, a 10 Newton force and a 4 Newton force. Okay, we can say that this object has a net force. The word net for us means total, or sum. A net force of, you know it? Do you know it? Do you know it? Yeah, 6 newtons. To the right. What will this object do? Well, this object accelerates. That's what we said before. The more important thing, sorry, not the more important thing, but equally important, is we should say in the direction of the net force. This symbol, sigma, means, for us mathematically, sum. Add up all of the. All right, so when we'll use most of the time, well, we'll always use that. I don't know, always, but we'll use symbols to represent big ideas. Okay, we have a thing like this. Come on, here's our object. Let's say that there's a that there is F1, F2, and let's say that F1 magnitude equals F2 magnitude equals, I don't know, 8 newtons. Well, the net force here is 0. I didn't make my F1 and my F2 look like they're the same size. My apologies. Better, right? Right. In this case, the net force is 0. Now, the only thing that we can say just on the case of forces alone is that, well, this object does not accelerate. Now, what can that mean? We got to think about what it means to accelerate or not accelerate. Well, if something doesn't accelerate, what does that mean? It means does not change velocity. Okay, if this thing does accelerate, it means it does change velocity. Now, those have to happen. A change of velocity has to happen, or can, I should say, happen in one of three ways. All right? So, what we can say is, one, this object could, one, speed up. Two, slow down. Three, tough one, remember? Change direction. Any one of those things could be happening. We don't know which one it is. It all depends on how the direction of the object's acceleration compares to the direction that it's currently moving. Right? If you move in one direction and also accelerate in that direction, you speed up. If you move in one direction and accelerate in the opposite direction, you slow down. And there's other ways that if you move in one direction but accelerate in a, well, not same or opposite direction, that can make you change direction. So in this case, if we say that an object does not change velocity, this object can't do any of those things. So what must it do? I'll say object must one of two things. Either not move at all, or two, if it is moving, move at a constant velocity. And what does that mean? That means move at a constant speed in a straight line. All right, so a major difference between what objects do based on what's happening to them. Go away. Come on. Stop. Okay, objects are either, any object that we look at is either going to have some non-zero net force, what we call non-zero net force, where there is a net force, or there's going to be a case where objects have zero net force acting on them. Okay? Now this case has a name. We call it equilibrium. And equilibrium means net force equals zero. Equilibrium means that objects don't accelerate. Equilibrium means that objects don't change velocity. All right, we're going to build a lot on each of these ideas. Objects that are in equilibrium and objects that accelerate. Those are opposite cases. Okay? Let's talk about a couple of other cases where the forces or their orientations aren't quite as simple. So let's look at a case like this where we have a force, let's call it 8 newtons. And we have a force like this, let's call it 6 newtons. Now, hopefully what we can tell is that this object, well, I'll say this explicitly, this object is not in equilibrium. What does that mean? Remember, equilibrium means that the net force is 0. So that means that the net force on this object is not 0. And how can we tell that? Well, we could take these two forces and add them tip to tail and find their resultant. And so this object has a net force. Still going to work? Nope, no paste. Clone. Copy. This is the same, or this thing will move the same way as this object. That has 10. How did we know that? All right, that's 6 squared plus 8 squared. The square root of 6 squared plus 8 squared. That's a Pythagorean theorem if we're assuming these are at a right angle, which we are. All right, so this thing has the same net force, or has a net force of 10 newtons that away. And what's the that away? We could do some trigonometry and find that angle. I believe it's 37 degrees, to tell you the truth. Okay? So, and then I'll say this. If we wanted to put this object in equilibrium, well, and this object being this object, the one with the 8 Newton force like this and the 6 Newton force like this, if we want to put that thing in equilibrium, well, like we said, the net force is this one, a 10 Newton force that's up at a 37-degree angle. Well, how do we put that thing in equilibrium? Well, we'd have to add a force that makes the net force equal to 0. Well, that would be a force that looks like this. It would have to be a 10 Newton force this way at 37 degrees in the completely, well, 37 degrees below the opposite horizontal, or a force that's, well, this force, right? Equal and opposite to the current net force, right? The current net force on this object over here is that 10 newtons up and to the right at 37 degrees. So to put it in equilibrium, we add a force that's 10 newtons down and to the left. Make sense? We good there? All right, next thing is if we look at a case like this, what will be very convenient for us, what do we name this? We'll say we need to be able to finding components of forces. All right, let's say that there's a force that looks like this. Let's call it F. And let's say that it points at an angle that we'll call theta as measured with respect to the horizontal. All right. Hopefully not that surprisingly, what we'll be interested in lots of cases are Fx, Fy, the x and y components of any force. All right. Gee, that sure looks like a whole lot like this analogous case. Here's an object that's launched at an initial velocity v0. Here is its horizontal velocity. Here's the vertical component of its initial velocity. And how do we find those components? Well, the same way we find these components. A vector is a vector. They just can measure different things. But this is just trigonometry, which allows us to talk about the relationships between these side lengths and angles. So, well, I'll just write it down. We've said before, let's not recreate the wheel. This is something that I hope we're getting really comfortable with. All right, that should be an automatic. and automatic. All right? And why do we want to do that? Well, what we want to be able to do in perpendicular directions. All right, the way our world works is that floors are flat, typically, right? The Earth looks pretty flat at our super zoomed in view. Gravity pulls down in our super zoomed in view, so that's, we're used to seeing things move on horizontal surfaces. We're used to seeing things that, that free fall and accelerate straight downward. And so what this defines for us in our natural world is a very typical set of coordinate directions that we can call the horizontal and the vertical. All right. So for us, if we see an object with any number of forces acting on it, what makes the most sense for us to do is to analyze what the net force in each of those directions is. Okay? We've talked about in our study of projectile motion that gravitational force, that downward force, affects vertical motion only, but not horizontal motion. Okay? Now, when we talk about forces, we're going to talk about objects that have forces acting on them in horizontal directions. And we want to look at how those forces in the horizontal direction can affect horizontal motion. All right? And so, what we need to be able to do is analyze a situation, like this. Let's say I'm going to put a few forces on here, and I'll sort of incrementally add them. So right now, what we want to be able to do is look at, the net force in perpendicular directions. And what I mean is in the x direction and in the y direction. All right, so what we will do in tons of cases is say that, we'll write expressions for the net force in the x direction and the net force in the y direction. Okay? Remember, what does net mean? This means add all of the forces in the x direction. Add all of the forces in the y direction. Okay, so right now, I'll erase this. You can write it down. What we want to talk about is what are all the forces in the x direction and how can we write them mathematically as a proper sum. Well, what I hope you can see is that A and B are involved in the x direction. All right? And if we use the typical convention that right is positive, I don't care if you want to make left positive, you go crazy, we would really say this is positive, and this is really, don't write this down, plus negative B. We're adding, but B points left. All right? So what we can most typically write this as is A minus B. That would be our net force in the x direction. All right? And right now there is no force, there are no forces in the y direction. Now, what about gravity? Isn't gravity there? Yeah, forget about that. All right? Let's say we're in deep space with a negligible gravitational field, and there are just these two forces, and so forget about gravity and stuff so far. That's why we're not saying that these are certain kinds of forces, A and B, we're just saying there's some arbitrary force. All right? Grouping, ungrouping. A, oh, come on, A might be better over here. Okay, now, what if I were to add a force, say, like this? C. So what does that affect? Does that affect our net force in the x direction? Well, it doesn't, because C is a vertical force. C is a force that points in this dimension, where let's call that way upward. So The only thing that would change is now the net force adding up all the forces in the vertical direction, the y direction. I just call this negative c. Fair enough? Okay, let's say that we add a fourth force, and let's say we added this one, D. And let's say that D pushes or pulls at some angle like that, theta, as measured from the horizontal. Now, what does that affect? Does that affect our x direction statement or our y direction statement? And when I say statement, I mean statement of all the forces acting on the object. Well, it actually affects both, because as we can hopefully see, D has an x component that we could draw like that. D has a y component that we can draw like that. So let's see. That would mean that it affects both, like we said. So over here in our x direction statement, what I'm going to do is, well, that would be add a dx. Dx points to the right. And over here, in our y direction, add a dy. Dy points up. All right? Okay, so let's go, one more step. I would rewrite this, if I'm being as thorough as possible, like that. That's how we express the x component of a vector. And over here, we can write negative c plus d sine theta. Might make more sense to write d sine theta minus c, same thing. All right? And again, the reason that we do x and y stuff is because, as we've led into, I hope, so far, well, remember, x direction forces can make objects accelerate in the x direction. Y direction forces can make objects accelerate in the y direction. All right? Y direction forces have nothing at all to do with what happens to an object's motion horizontally. Horizontal forces have nothing at all to do with what an object does or what its movement, what its motion is like vertically. So it's important for us to really separate those quantities, and that's why it's so important in our look at projectile motion. Okay? Now, we've been speaking in very, very arbitrary terms so far, and so what we'll do now to wrap this up is talk about 5 of the most common forces that we're going to deal with really at all this, in this unit at least. Okay, there will be some more that pop up later on, but I will call these our 5 forces. All right. I use this acronym, or this mnemonic. I want my forces. Who doesn't? Right? So this WANTF. It's a nice way, well, maybe, to remind yourself of what forces there might or might not be acting on any object. All right. So W. There's a force that starts with a letter W. Weight. An object's weight is a force. In particular, it's the force that gravitational fields exert on every object. All right. Well, then there's an A. Give me an A. A. Give me an N. N. So A. What's an A force? People say acceleration. Well, acceleration is not a force. Acceleration is the rate of change of velocity. Acceleration is not a push or a pull. It's the result. It can be the result of a push or a pull. All right, so A, this is what we use to abbreviate applied force. And an applied force is a push. That any object can experience from contact with another object. Give me an N. N. N is the hard one. N is called a normal force. These should be in caps, shouldn't they? Of course they should. Applied. Oh man, of course that would happen. So a normal force is what we call a reaction force. That any object can experience that any object experiences when in contact with a surface. All right, so here's the deal. Here's a tabletop. Here's a box on that table. Well, this object experiences a gravitational force due to the gravitational field. Let's say, if we're talking in this room, the Earth's gravitational field is such that it applies, well, what we call a gravitational force. We could also write that or W, or FW. I write it as FG, gravitational force. It's really the object's weight. And that force of gravity pulls this object down onto the table. So object pushes on table. Well, if object pushes on table, then table pushes on object. There's a force N. Notice the size I've drawn them. It's not perfect, but if you look at a box on a table, the box on the table is not moving relative to the table. And therefore, it is not accelerating. And therefore, at least in this case, not always true, but in this case, the normal force is equal in magnitude to the gravitational force. It's the same as the object's weight. Not always true, but it is true in this case. Okay, so I'll just qualify this. I'll say object pushes on table. Therefore, for me, 3 dots in a triangle means therefore. Therefore, table pushes on object. Big parentheses. Some of you might have heard a rule, that some sort of law that sounds like that, especially when you think about it in that context. Okay. Now, let's see. Next, give me a T. T. The T force tension. All right? And tension is a pull from a rope, chain, cable, string, anything else, thread, bungee cord. All right? And finally, give me an F. F, any guesses? I can hear you. You yell loud enough. Friction. Friction's a tough one. Friction is for force that objects can experience when in contact with surfaces. Oops, surfaces. But it's not the same thing as a normal, all right? Let's see. The thing about friction is, I mean, people usually think about friction as slowing things down. Well, sometimes it does that. Doesn't always do that. Friction can actually make things slow down or speed up or change direction, or it can keep them from moving. Friction can do lots of things. But I will say always acts in direction opposite intended motion. Now, saying intended means that objects have intention and they don't. That's called anthropomorphization or something. You know what I'm talking about, right? But the deal is friction can happen if some other force is making an object, would otherwise make an object move. And friction will oppose that. Okay? We'll talk a whole bunch about friction. All right, those are the 5 forces. All right, notice there's 2 main categories. There are forces that fields exert. There are 3 kinds of, I hope there are 3 kinds of fields that we'll talk about. There are gravitational fields, there are electric fields, there are magnetic fields, and those fields can exert forces on other objects depending on their characteristics. All right? And then you notice that the other kind, contact and contact and contact. Yep, contact. I didn't write it here, but you know the rope's got to be in contact with the object. So there are contact forces and field forces. All right. The contact ones are easy because you can see 2 things and touching each other. The field forces are can be trickier because you can't see why they happen, but they do. Okay. Last thing is this: some rules about specific forces. There are 3 for weight or gravitational force. All right, gravitational force always points down. When we say down, you know what we really mean by down. And again, let's talk about, we're talking about here near the surface of the Earth, let's say for now. Down really means toward center of Earth. There'll be a time when we talk about more macroscopic views of the solar system or the universe, and then we'll talk about, I mean, really what direction the gravitational forces point. They point in the direction of the net gravitational field, but we haven't gotten to that quite yet. Okay? So any and every time you draw a gravitational field, a gravitational force, for now, just draw it straight down. Okay? That's one. Applied forces can be in any direction you want. You can push an object any direction you want. Okay? Normal forces, not N for newtons, N for normal, they are always perpendicular to surfaces. All right, so like we showed a little bit ago, here's a surface Here's an object on the surface. The normal force points like that. Okay? Here's me leaning up against the wall. That's bad. Leaning up against the wall. What was it? Whoops. Darn it. Yeah, leaning up against the wall. Come on, man. Yeah. And here's the floor. Well, there's a couple normal forces acting on me. One is there's a normal force like this. Wall pushes me that way. Another one is this. I'll call that normal wall. I'll call that normal floor. Okay? Here's another case. Here's an object on an incline. Normal force points perpendicular to surface. This symbol, the two lines that are perpendicular, means perpendicular. Okay? Tensions, ropes. You pull an object any old direction you want. No rules about tension forces. But friction forces, these I typically, most of the time, do F with a subscript F. I don't just want to write F because then you might just say, that might just mean force. We want to make sure we're talking about a friction force, so I do F with a subscript F. If you want to write F with a subscript N for that, be my guest. All right? I just write N. Whatever you want. All right, these are always, well, let's see. Let's say that we have an object like this, and it's being pushed this way by an applied force. Well, by definition, there's going to be a friction force that points that way. How big depends on some other stuff. Okay? Let's say that there's an object that's at rest on an incline. Well, how can that happen? Well, it can happen if there's enough friction that points, in this case, up the hill. Right? Here's a case where friction acting on a moving object. Here's a case where friction keeps an object from moving. All right? What else could you do? There's any number of situations. But the big deal is that friction forces are always parallel to surface. Okay? They always point right along the surface. Normal forces are always perpendicular. Those are the rules about directions that different forces have to point. All right, these are the 5 actual forces that we'll deal with the most, at least in this beginning part of the the beginning part of the unit. Okay, or really for this whole unit. Okay, we spent a good bit of time talking about net force, the idea that what net force acts on an object is the entire phenomenon that controls why its motion is like it is. All right, so lots of different ways to add up forces. We want to be able to look at them. They're combinations in one of 2 directions, either the horizontal x direction or the vertical y direction. There's a refresher on how we take a force that's pointing at an angle and look at its components. Here's a case where we can look at forces that are not linear, not collinear. They're not in the same dimension like these 2 6 and 8 Newton forces. We can use Pythagorean theorem if they're perpendicular to find their resultant. All right. Over here on the right, we said, well, if there's a certain net force on an object now, what would we have to do to put it in equilibrium? All right. What would we have to do to make the net force 0? So we talked about that idea of equilibrium. That's a case where all of the forces acting on an object add up to nothing. But then there's the opposite case of that, where we could have 2 forces like the 10 and the 4 Newton force here that don't add up to 0. Well, and what we said is the big, huge difference is that if an object has a non-zero net force acting on it, like this one on the left, the object accelerates by definition. If an object has a zero net force, there are either no forces acting on an object or they all add up to zero, the objects can't accelerate. We made sure we touched on what acceleration can mean. Speeding up, slowing down, or changing direction. So an object, in order to do any of those three things, has to have a non-zero net force acting on it. Okay? And then, yeah, this is the crux of it all. Why do objects move the way they move? They do because of how the forces acting on them combine and add up. Okay? So a lot there, a good base. We'll work from it. See you soon.